Okay, picture this. You're on a bullet train just blazing along at 500 kilometers an hour, and your video call is perfect. No glitches, no buffering. That's the dream of 6G, right? Well, today we're digging into a research paper that might just be the blueprint for making that dream a reality.
We sure are. We're unpacking spectrum and orthogonality of orthogonal delay-Doppler division multiplexing modulation. And this is a really impressive piece of work. It's led by first author Akram Shafii, and it's a major collaboration between researchers at the University of New South Wales, the University of Wollongong, and even industry pros over at Telstra. So, Alex, where do we start?
All right, here's the game plan. First, we're going to talk about the big problem, why today's tech just can't keep up with extreme speeds. Then, we'll introduce the star of the show, ODDM. After that, we'll look at the two different ways you can actually build this thing, see how they measure up, and put it all in context with its relatives in the 6G family. And stick around, because you're going to see why sometimes the simplest solution is actually the best. Okay, let's set the scene. 5G feels blazing fast for most of us right now. But what happens when you're not just sitting on your couch? What about a self-driving car talking to another car on the highway? Or that bullet train we mentioned? Can 5G actually handle that? And that, right there, is the million-dollar or probably billion-dollar question. Look, the tech behind 4G and 5G is called OFDM, and it's an absolute work of art. But it has an Achilles heel, really, really high speed. It's kind of like trying to read a street sign from a race car. The letters just blur together into an unreadable smear.
And that smear is basically what the Doppler effect does to our data signals, right? It just blurs everything together.
Exactly. The perfect separation between all those little bits of data, the very thing that makes OFDM work so well, it just completely falls apart. So the challenge is pretty clear, isn't it? If we want a 6G future with cars that talk to each other and lightning-fast trains, we need to figure out how to build a network that won't get blurry when things start moving fast. Well, thankfully, some very smart people are working on this, and the answer might come from a whole new way of looking at the problem. It's a technology called orthogonal delay-Doppler division multiplexing, or let's just call it ODDM for short. So what's the big deal with ODDM? Well, instead of trying to fight the physics of that high-speed blur, it actually uses it to its advantage. Think of it this way. You're in a huge, noisy stadium trying to find your friend. You could try to look for their face, which is almost impossible. Or you could listen for the unique sound of their voice and which direction it's coming from.
That's the delayed Doppler plane. It's just a much more natural way to find a signal in all that chaos. ODDM is basically designed to speak the native language of a fast-moving channel.
That is a perfect way to put it. It's built from the ground up to thrive in these messy environments. And we should definitely give credit where it's due. The core idea for ODDM came from two researchers, Hai Lin and Jinhong Yuan.
Absolutely. So with this amazing concept out there, the authors of this paper came along and asked the next logical and super important question. Okay, this is a great idea, but how do we actually build it? And does it work as well in practice as it does on paper? And that's what we're here to talk about. They explore two totally different ways to bring ODDM to life, a pure analog version and a really clever digital one.
All right, two blueprints on the table. Let's start with the old school way. Alex, walk us through the analog approach. What does that even look like? Okay, so this is the purist's approach. It's the most direct way to create the signal. Just look at all the physical parts involved here. You've got tons of these little components called mixers, you've got pulse shaping windows, multiplexers to combine everything. It's a really intricate, complex piece of hardware, all designed to create that theoretically perfect OMDM waveform.
Intricate is one word for it. The paper notes that for a big system, you'd need something like 200 million mixers. That is just a mind-boggling amount of complicated and probably expensive hardware.
So how on earth does the digital version get around all that complexity?
It's all about working smarter, not harder. The analog way is like a master watchmaker, handcrafting every tiny gear and spring. The digital way is like using a super advanced 3D printer. You just give it a digital file, and it creates the whole thing in one go. It actually is the same math trick as today's OFDM, the inverse fast Fourier transform, to do all the complicated work in software before a physical radio wave is ever even created.
And this really boils it all down. On one hand, you've got the analog method. It's pure, but it's a monster of hardware complexity.
And on the other, you've got the digital method. Yeah, it's technically an approximation, but it swaps out all that messy hardware for clean, elegant software. It's the classic brains versus brawn showdown. So the big question is, which one actually works better?
Exactly. You've got these two totally different ways of making a signal, but do they act the same when you send them out into the real world? To figure that out, this paper goes deep on two absolutely critical properties: what the signal's spectrum looks like, and this crucial idea called orthogonality. And you know what? Right off the bat, they found something really interesting. This graph is basically a picture of the signal's energy, its power spectral density, and you can see the difference immediately.
Whoa, yeah. That analog ODDM on the left, it's got these weird, jagged, step-like edges. What's that about?
It's just a side effect of how it's physically built. But now look at the digital ODDM on the right. See how much smoother and cleaner it is? It's just a much more well-behaved signal. Okay, it's definitely a clear visual difference. But does a prettier signal actually matter? I mean, do they perform any differently? Does the shape of that signal affect its ability to keep all the data from crashing into each other? And that, my friend, is the most important question you can ask. That's orthogonality. It is the absolute magic that makes all modern wireless communication possible. Think of a massive highway with millions of cars. Orthogonality is what paints the white lines on the road, making sure every single car stays in its own lane and nobody crashes. Without it, you just have chaos. And this is where we get to one of the paper's biggest mic drop moments. They proved that the simpler, cleaner digital ODDM achieves that perfect orthogonality. No crashes.
Yes, and it does it more efficiently. The paper shows that to get that same perfect performance, the analog version might need extra safety features, stuff like cyclic prefixes. It's like a car that needs giant, clunky bumpers to keep from hitting things, but the digital ODDM, it's just so cleanly designed, it doesn't need them. It's just inherently better.
Now, this is where it gets really interesting. ODDM is a huge contender for 6G, for sure, but it's not the only game in town. There's a whole family of technologies all based on this Delay-Doppler idea. To really appreciate what makes ODDM special, we kind of have to see how it compares to its famous cousin, OTFS, and the rest of the family. Okay, Alex, I'm not gonna lie, this table looks intimidating. There's a lot going on here. Where do we even start with this thing?
It is a lot, I know. But let's zoom in on the most important column here, the last one, labeled order. It's just showing us a choice. Do you do windowing first, then pulse shaping? That's W arrow PS. Or do you do it the other way around?
Okay, what does that even mean? Why does the order of operations matter so much?
Let me give you an analogy. Pulse shaping is like picking a really elegant, smooth font for your text. Windowing is like taking a pair of scissors and cutting out a specific shape from your paper. Now, if you type your beautiful text and then take your scissors and cut it out, that's pulse shaping, then windowing, you're going to get sharp, jagged edges where the scissors cut through the letters. And in the world of radio signals, those jagged edges are bad. They cause interference, what engineers call out-of-band emissions, or OOBE.
Ah, I get it. So you're basically spilling your signal into the lanes next to you, causing noise for everyone else. What happens if you flip the order?
And this is the genius move. If you first cut out your perfect shape with the scissors, the window, and then you carefully write your elegant text inside those boundaries, that's windowing then pulse shaping, the result, a perfectly clean shape with no jagged edges. Now look at the table. Digital ODDM makes that exact choice, W then PS. Its main rival, digital OTFS, does the opposite, and that single choice has a massive impact on how clean the signal is.
That's a great way to explain it. So it's a fundamental design choice. What else does this table tell us?
Check out the domain changes column. This is the path the data takes to become a signal. See how both digital ODDM and digital OTFS go from the Delay-Doppler domain to the time domain? That's the path that lets them use that super efficient IFFT math we talked about. But look at some of the others, like ZAC-OTFS. They take different, more complicated routes that need different, more complex math to work.
So ODDM's path is simpler and its process is cleaner. Wow. Laying it out like this really shows that these aren't just minor differences. The design of digital ODDM seems to be the result of some very specific and very smart choices that really make it stand out.
Exactly. So after all of this, I mean, this incredibly deep dive comparing the different blueprints, the shapes of the signals, the whole family tree, what's the bottom line? Which one actually wins? Let's get to the final verdict. You know, the paper's conclusions just lay it all out so clearly. 1, they proved the digital version has a much cleaner signal. 2, they showed it's way more efficient at preventing interference. And 3, The knockout punch, their simulations show that it performs just as well, the bit error rate is the same, as the super complex analog version.
It's like a clean sweep for the digital approach.
It really is. You get the same performance, a cleaner signal, better efficiency, all with a tiny fraction of the complexity. That's not just a small win, that's a huge deal for anyone who has to actually build this stuff. And you know what? Let's just let the authors themselves have the final say. They put it perfectly in their conclusion, and I'm quoting here. The approximate digital ODDM system achieves similar BER performance compared to its analog counterpart while requiring significantly lower implementation complexity. It's right there. You get all of the gain with none of the pain. So, I guess this leaves us with one big question to chew on. Is this where wireless is headed? Are we seeing the end of the line for these incredibly complex, hardware-heavy designs and the beginning of an era where it's all about clever software?
This paper makes a really, really strong argument that it is. But of course, the final chapter for 6G hasn't been written yet. It's groundbreaking research just like this that's going to write it. Thanks for tuning in, everyone.